The North American Society for the Psychology of Sport and Physical Activity, NASPSPA, will celebrate its 50th anniversary in June of 2017. As part of the celebrations, it was decided that we would interview the previous distinguished scholars. My name is Penny McCullough, and today I will be chatting with Dr. J.A. Scott Kelso. Through 2016, NASPSPA has named 24 distinguished scholars. Dr. Kelso was named a distinguished scholar in 1999. This interview is being conducted in March of 2017. Good afternoon, Dr. Kelso. How are you today?
Good afternoon, Dr. McCullough. I'm very well.
Excellent. So, first let's start out. Please tell us a little bit about your academic background.
Well, my academic background is rather checkered. I grew up in Derry, or Londonderry, in the northwest of Ireland. Our house was located on the Academy Road, so there was a strong academic kind of interest in things. I went to the model school, and then after passing an exam at about the age of 11 or 10, I went to Foyle College, which was a local grammar school. Both schools were close to home, and I walked to school every day. So when I was young, I was really more interested in music and drama. I did some singing on BBC radio and TV for a number of years, and then played parts in school plays. People like Beckett and T.S. Eliot's Murder in the Cathedral, and Antony and Julius Caesar, and even at the age of 17 years old, I played Antigone and Jean-Henri's Antigone. So what I didn't realize at the time is that this was good training for public speaking and lecturing, as I later found out. As well, I think, as for training memory. So anyway, at a certain point in time, my parents consulted the headmaster of the grammar school and asked him what he would recommend their son to do as a career. And he looked at my grades and said, well, he's pretty good at science and math, and it's very difficult to make a living in the arts, so he wouldn't advise me to do that. And so maybe he said I should become a doctor. And that was called career counseling in those days, and it happened to fit my mother's desires as well, but not particularly mine. I was very keen on sports, mad keen on sports, particularly rugby, football, and cricket, but basically anything with the ball. So this brings me closer to NASPSPA, I guess. Although I was offered a place in medical school, I was really keen to play for Ireland at sports, and so I decided rather focus on sports. And the best way to do that was to train as a teacher in Stranmillis College. It's now Stranmillis University College. It's attached to Queen's University in Belfast in Northern Ireland. And there, at the time, the best rugby coach in Ireland was a man called Mr. Lapsley, Mr. Josh Lapsley, who was a lecturer there on motor skill learning. And he became my mentor. So I did that for 4 years, and then taught English and math for a year or two in a very good school in Northern Ireland, and coached as well. So a very keen interest in movement. I captained my college rugby team on a tour to Western Canada. I made some good friends there, especially in Calgary, Alberta, where a man called Peter Reichenbach, Dr. Peter Reichenbach, who was an Australian, was assistant head of the phys ed department there. And Peter encouraged me to come out to the University of Calgary to study. So at some point, curiosity got the better of me. I think things were heating up in Northern Ireland with the Troubles, where I was teaching, and attitudes weren't changing anytime soon. So I decided to leave Ireland and pursue academic studies more seriously. So after a year in Calgary, where I studied mostly physiology and psychology, I was advised and encouraged by one of my professors, a man called Dr. Barry Kerr, to go on to graduate school in Madison, Wisconsin in 1972. Also, I'd been taught by Dr. Jerry Ells, who was a former PhD student of Michael Tozer at Oregon. And both of them were very, very encouraging of me to do academic studies and to do research. I think as a graduate of the University of Wisconsin-Madison himself, Barry must have written a glowing letter because I was accepted and awarded a stipend of something like $1,500 per year. That was a lot of money in 1972, I guess. Anyway, it wasn't too clear to me which area I wanted to study. I guess you were going to ask me about that, Penny.
Yes.
But that's a little bit about how I got to Wisconsin. And then, of course, Wisconsin is another story about, how I ended up doing what I do, I wasn't really very clear about that when I went to Wisconsin. I think I had two options. I was very interested in physiology, and so one of these options was respiratory physiology with someone called Dr. Jerry Dempsey, and the other was motor behavior with Dr. George Stelmach. I really was very keen on both areas, but with a full course load and working in two labs, something I could give, I guess. And my stipend was coming through Dr. Stelmach, and he was a new professor at Madison at the time. So it was decided that I should work primarily with him for a while, and Dr. Dempsey was very busy in the medical school. And George, because he was a new professor, was able to give me his full attention. We'd meet for coffee every day and talk about ideas. I suppose it was a bit formal and a bit intimidating, but the one-on-one with George was a great experience, and I learned a lot. So I was George Stelmach first, and at the time, I was only graduate students. So even as early as the first semester, I was running experiments in short-term motor memory, which was George's main interest at the time. George would help me write up my ideas for experiments, which was very good training for something that I didn't really know too much about, which was writing grant proposals and the whole world of research funding that I really no idea about. So this was very, very important training. At the time, I guess linear positioning studies dominated the field of motor behavior. And although I have to say I wondered what this had to do with movement and skill learning, I loved working in the lab, and I loved the scientific method. I loved the history of science. I loved designing experiments. I loved the quantitative and statistical aspects of data analysis, and it was like a whole new playground for me. So that was really the way, I came to work with Dr. Stelmach. And during the course of that first year, I'd become very interested in kinesthesis, the so-called forgotten sense of movement. And in our readings, I'd come across a technique that Judith Laszlo had used to eliminate touch and movement sensation. This was, I suppose, it was much more on the neurophysiological side of things, which really appealed to me. And I wondered, I was curious actually, given the relative size and conduction velocities of motor neurons and sensory variants, I just wondered how selective Laszlo's nerve block technique was. So I ended up doing my master's thesis with the late Dr. William Bill Wanamaker, who was in the Madison Department of Neurology. So I wound up in Bill's lab, and he taught me how to stimulate the nerves of people supramaximally across the nerve block, and I recruited people from the local rugby team, actually, to measure the conduction velocity across the nerve block, and I found that the sensory motor nerves were both pretty much blocked at the same time. On the behavioral side, subjects couldn't feel anything, but they couldn't move either. So that was kind of fun. So where are we in this now?
What?
You have a question?
Well, I think you've answered the first two or three questions. I think you've answered the first two or three questions pretty well. Tell us a little bit about your doctoral dissertation.
Yeah. Well, around the same time, I was taking a lot of coursework in psychology, and one of these was on experimental perception with the eminent perceptual psychologist, William Epstein. And I had the idea, actually this wasn't part of my thesis, but Epstein ended up being on my committee, my doctoral dissertation committee. But I had the idea that the received wisdom at the time was that vision dominates touch. And I had the idea that that might be due, at least in part, to how hard subjects attended to where they saw their limb relative to where they felt it. So we tested that in a course, actually, on experimental perception, and experiments worked out very nicely. So well, actually, that the paper got accepted for publication in the Journal of Experimental Psychology, and Dr. Michael Posner was the editor at the time. So I really enjoyed getting my fingers wet in all this research, and of course, the fact that the research was worthy of publication made me feel that even as a lowly graduate student, it was possible to make a scientific contribution. I find the intuitive, the conceptual aspects of research as well as the details. I find these both equally challenging, and I was very fortunate to have such devoted professors. I think they also realized they had a curious Irishman on their hands who was keen to learn new things and wasn't really afraid of work. So for my doctoral dissertation, I continued on with the modified nerve block that had been developed in Oxford in Professor Peter Matthews' laboratory of physiology. And this modified nerve block allowed one to block off sensation in the hand while preserving the muscles in the forearm. And the muscles in the forearm move the fingers. So I found then that subjects could locate their limbs in space quite accurately, even though they did not know where they were starting from. And it turned out that similar experiments have been done with deafferented monkeys. But I interpreted my results in terms of an idea from Anatol Feldman, who was a Soviet-Russian experimenter at the time, which had to do with sort of dynamic models, mass spring, equilibrium-seeking models. Feldman's experiment involved, I guess, perturbing, you held your limb at a given posture and perturbed it. So they were a bit static. My experiments, and actually it's really one of my main interests, involved intentional movements to self-selected targets. So although the conclusions were similar to Feldman's and favored the mass spring equilibrium-seeking model, where the way that works is sort of the idea is that the nervous system sets the parameters and the dynamics do the rest. So in my dissertation, I did the same study in patients also who had their finger joints surgically replaced with similar results. And again, Wisconsin was such a great place. The eminent orthopedic surgeon, Dr. Andrew Macbeth, was in the UW Medical School there, and he helped me get access to the patients. These patients didn't have any joint receptors and stuff after they've had their finger joints removed, and so I was able to observe them actually doing the operation, and that was a great experience. So that was basically up to the end of the doctoral dissertation, and it was onward from there, I guess, Penny. Yeah.
Okay, that's great. Well, you say you had some pretty dedicated professors. Well, I think they had a pretty dedicated student as well, so it was beneficial to all, it sounds like.
Yeah, I think I was a little, I took the work very seriously, actually, but that's always been my philosophy, work hard and play hard, and you need both of them, in my view. One without the other isn't much of a life. Anyway, so...
Dr. Kelso,
Yep.
Yes. Okay, so your distinction of becoming a Distinguished Scholar of NASPA, and you did that fairly early on, recognizes your long-standing contributions to areas of research represented by NASPA. We now want to talk a little bit more about your scholarly endeavors. So let's start out. You've told us a little bit, but let's carry on, if we can, a little bit on what sort of research interests did you have early on? Did you continue to pursue that same line, or if you changed, tell us a little bit about how that happened.
Yeah, well, that, chance sort of favors the prepared mind kind of thing, Penny.
Could you adjust your phone just a little bit? Yes, could you adjust your phone just a little bit? Okay.
Does that help?
Yes.
Is that any better?
That's a little bit better.
Yeah. This is a new phone, so can you hear me better now?
Yes, that's better.
Okay. So anyway, related to the whole issue of how one's research interests evolved, again, it's always connected to one's life. And my first job was at the University of Iowa, and now I had my own lab and was doing the teaching as well, actually, 9 credit hours per semester. So how this kind of evolved was that the National Science Foundation had a program to improve undergraduate education. And I thought it would be neat to bring in experts for a series of lectures, just kind of like what you're doing here, record the lectures, edit them, and prepare a new textbook. So the beauty of this idea was that I was able to recruit the top people in the field. Not only have them give a full week of 5 lectures, 1 per day, but then had the opportunity to interact with the best minds of the field at the time. And then as I bought into that idea, and although Dr. Jack Adams wasn't able to come, Richard Schmidt, Dick Schmidt, and George Stelmach, Stephen Keel, Anne Gentile, and Mike Turvey were kind enough to accept the invitation, and we just had a fantastic time. So they came in one at a time, by the way. It wasn't they all came in together. They came in one at a time for an entire week. So it was a great one-on-one experience for my graduate students and myself. So out of that came, some ideas. In particular, we were reading Michael Turvey's paper on, it was called something like Preliminaries to a Theory of Action, with reference to vision. I think that was the title. It was a very difficult paper. Turvey was trying to put Gibson's theory of perception and mostly Russian research on locomotion together. It was very hard to understand this at first, but despite, by the way, Turvey's eloquence as a writer and lecturer, but it was very novel and incredibly stimulating and intellectually, I think, very challenging. Anyway, one of the main ideas that emerged was to use what Nikolai Bernstein had called synergies. Actually, Sherrington used the same word, with the idea that synergies reduce the problem of controlling the many degrees of freedom of the locomotor apparatus. So obviously walking, even though it seems very simple and natural, involves very, very many degrees of freedom, neural elements, muscular elements, joint elements. They have to be somehow controlled and coordinated. Now, most of the work on locomotion was actually on decerebrate cats. That's just cats without a brain, basically. And I was curious, well, could the same idea be used for the voluntary movements of human beings, which is really what I was after. I wanted to understand how humans make voluntary movements. It's a great question, I think. It hasn't really been answered very well. So I thought, well, maybe synergies are involved in that as well. So as I said, all the work going on in motor behavior at the time was using simple linear positioning or reaction time tasks. And we're aimed really, for example, at testing Adams' closed loop theory. A lot of people got into that, or various ideas about motor programming. So in the graduate seminar that was tied to the visits of these people, we were discussing some of this in relation to Fitt's law. And one of the students, Dan Sullard, asked, what about two-handed movements? So how does Fitt's law work when you use two-handed movements? And Dan produced two pieces of material out of his pocket as targets, and we did the experiment right on the spot. And of course, there was a bit more to it than that. I wanted to see what the movements themselves looked like, how it was done. So we used a pulsed light-emitting diode technique, which was borrowed from biomechanics, along with high-speed photography, to actually record the trajectories that people were doing in this task. And that was followed, actually, by painstaking frame-by-frame analysis to calculate the kinematics of the movements. This was long before computerized systems for motion analysis existed. And this kind of frame-by-frame analysis was really cool. It showed that the two limbs, even though the limbs were moving to targets of different difficulty, what Fitz had called the index of difficulty, he used an information theoretic measure to quantify the difficulty of different movements, how far you have to move, how precisely you have to move, that kind of thing. And what we find is that even though the two limbs were going to different difficulty targets, they initiated and arrived at the same time. So this was very suggestive that what we call, synergies or functional synergies, actually, this kind of organization of the motor apparatus is likely to be exploited by the brain to control and regulate voluntary movements. And so that was a completely new direction that set me off in an entirely different direction. And I think, in part because it was accepted for publication, it was published in Science, it attracted a lot of interest in the broader scientific community as well. So this little experiment, along with the detailed analysis, that's my other phone, I'm sorry about that. Anyway, so this then became the whole idea that the brain was using these functional synergies, or we call them coordinative structures, I like that term, which we hypothesized were the basic units of biological movement coordination. And actually, I think probably the basic units of biological coordination in general, actually. So this now opened a whole new can of worms. So it set my research off on complex movements, really, and it set me off in an entirely new direction, in part, I think, because the paper had been accepted in Science and attracted a lot of interest. So new opportunities arose, and around this time, I moved from Iowa to Haskins Laboratory at Yale University. Actually, Iowa had offered me tenure after 2 years, but I just decided I wanted to learn more. And at Yale, at Haskins, the main scientific focus was on the relationship between speech perception and speech production. And I'd never studied either of these things, but I was very interested in speech and language historically, just as an example of really skilled, coordinated movement. And the Haskins approach was multidisciplinary, which I liked a lot because I could learn a lot. They had physicists and engineers and psychologists and linguists all involved in trying to solve the basic problem of how we perceive and produce speech. So the very background and quality of the scientists at Haskins was extraordinary. And this, along with their exceptional technical and scientific support, it offered a totally new learning experience for me. And it sort of took me almost away from the field of motor behavior per se into a broader picture of science and in particular how perception and production were related. The speech production system, as you well know, was extremely complex. So let me just say that to say a simple syllable like ba, ba requires the coordination of a large number of muscles at respiratory, laryngeal, supralaryngeal levels, and many time scales. So it was a real wonderful problem of biological coordination and natural biological coordination in a system with very many degrees of freedom. So it's a miracle of movement control. Again, babies do it spontaneously, but we all take it for granted, as it were. So the speech production then seemed a perfect candidate to test this synergy hypothesis, namely that the way the biology handles these complex systems is to synergize them. So one of the hallmarks of a synergy is that if you perturb the system unexpectedly, it should be compensated very quickly by remote members of the synergy, of the putative synergy, so that if you unexpectedly perturb one part, the other parts would respond in such a way that you would be still able to achieve the goal. The system's functional integrity would be preserved. So that was, following the rather technical two-handed movement work that we had published in Science, this was even more technically challenging because now you had to put in intramuscular electrodes into the muscles of the tongue and the lips and the jaw and do continuous recordings, and then you had to have a way to perturb the jaw so that if the person was saying ba or whatever syllable, you could look at how the different muscles in the tongue and the lips and the larynx, depending on the particular speech context, that's to say what sound the person was trying to produce, those articulators are going to be selectively recruited depending on the context, what they're trying to say. And so this idea that you challenge one member of the synergy of the putative synergy, because the synergy hypothesis, as it were, and the articulators are potentially independent. They're not necessarily coordinated. But the idea is if you perturb one member, then the others should meet the perturbation by responding selectively, even on the very first perturbation experience. That is, you'd never, this is not a common thing, you know, when you're speaking to, say, the syllable ba or baz or something like that, that suddenly the jaw is perturbed, and the jaw normally raises when you want to say bab, you know, it lowers and then it raises, or if you want to say baz, the tongue has to get to the roof of the mouth. And so, depending on the context, actually, the same perturbation produced entirely different kinds of effects, but always in a way that it preserved the intent of the speaker. And this kind of was the first, I think, well, direct evidence that these coordinative structures are sort of the basic units of coordination. So that then was, you know, raised then the whole issue of how on earth these synergies that you're calling synergies, or how are they formed, how do they change, how do they adapt. So that's a whole new research program. And that's really then, you know, if the synergy hypothesis is a hypothesis about how nature sort of handles this kind of biological complexity, where the system contains very large numbers of degrees of freedom, then how are these synergies formed? And you know, it didn't seem likely that the brain was a computer here, that you had pre-prepared programs and stuff. This was spontaneous. It was adaptive. It was just a different kind of thing than a programmable device. So then now, where do you get the ideas for how nature handles biological complexity? And nowhere in the field of movement, or actually in neuroscience, or really were there ideas about this. You know, Sherrington had the idea of reflexes, and Von Holst and other people had the idea that pattern generators, you know, of motor programs and stuff. And of course, in the behavioral literature, people like Dick Schmidt had talked a lot about motor programs and even schemas for movement and stuff. But the whole issue of how these synergies might be formed, how they change, how they adapt, that was wide open, and it needed a conceptual change as well, not just an empirical change. So this again goes back to my earlier remarks that really I always was keen on to learn what new concepts might be necessary to handle the whole issue of skilled movement. And so around that time, there was work going on in physics and chemistry, particularly. You know, you see, I'm now at Haskins, and you're in the field of science, you know, and you read about science a lot, and it's a broader picture than, you know, reading the Journal of Motor Behavior. There's nothing wrong with the Journal of Motor Behavior, but it's a much broader picture. And a man called Ilya Prigogine had won the Nobel Prize in 1977 for what he called dissipative structures. And these are spontaneous formations of structure in systems that are not at equilibrium. So here was nature with these, you know, enormous numbers of microscopic degrees of freedom under certain conditions, under open conditions where the system can interchange with its environment, exchange matter and information with the environment, that you'd get this sudden emergence of new forms of behavior. And physicists have called this phase transitions. And these were phase transitions in non-equilibrium systems. So these phase transitions deal with how matter changes, like, you know, from liquid to solid, from solid to gas, that kind of thing. So the dangerous idea I had was, well, maybe, you know, movement is like this, biological movement is like this as well. And, you know, I thought, well, what about, you know, animals, like horses? I mean, I'd grown up near in a farming community and knew quite a lot about quadrupedal creatures. And Of course, quadrupeds change gait. So they move from, walking to trotting to galloping. Actually, quadrupeds have a large number of gaits, more than you'd imagine. But the idea was that these gaits, when you switch from one to the other, that's analogous to a phase transition in matter. And that was the idea. So the idea was that, and physicists gave that a name. They call it self-organization. So this is sort of the dangerous idea, as it were, that this doesn't mean that the self is doing the organizing like a programmable computer or something like that. It meant that the system is organizing itself under certain conditions. So, and these transitions were evidence that this kind of self-organization was going on, and it's a name, self-organization, given to complex systems in physics and chemistry that are composed of, very many interacting parts. And the idea is that under certain conditions, these patterns form spontaneously. They form spatial structures, temporal structures, and so on. So this is what people now call emergence. So it's emergent physical phenomena that's really regulated by higher order principles than, say, the basic laws of quantum mechanics, that kind of thing. So it was a very profound revolution in the study of matter that was taking place. And I wondered where the study of function, whether that might be analogous. And so that was the idea. But then, I took that into, I had an idea. It was one night late in the lab. In those days, we had yellow pages for phone books, all your contact information wasn't in your phone, you looked it up. And one of the ads was, let your fingers do the walking, you see. So I thought, well, let me try that. I still get a bit of a chill when I think about it, and it gives me the chills just talking about it. But so I sort of, with my index fingers, my middle fingers, with two hands, sort of created a quadruped. And I find, very simple manipulation of speeding it up, like when the animal has to go faster, it switches from a trot to a gallop kind of thing, the same kind of thing when you do it with your fingers. So this is amazing. And, I was in a speech laboratory, I wasn't doing, although they were, I must say that people taskings were quite happy for me to pursue ordinary limb movements as well as windows into more complicated things like speech. But here was a little model system, and that's kind of the sort of paradigmatic idea here, that you try, that science doesn't look at the whole thing. It tries to find sort of model systems that it can say something, quantitatively about, and maybe generalized from there. So I was going from phase transitions of matter to equine transitions of gait, then to fingers doing the walking. So these were the kind of thought processes somehow going on, And it turned out that actually all the signature features of these non-equilibrium phase transitions were observed in the finger movement studies. And that was, sort of a real paradigmatic change, So what happened is that, if you move your fingers in a certain way, if you start off sort of anti-phase, you're moving rhythmically, so rhythmic movements were the kind of a platform for this. And if you go a little bit faster, then there's an involuntary, spontaneous change from one pattern to the other. And when you really look closely experimentally, and, by this time I had a whole number of, really very excellent students like John Schultz and Bruce Kay and people like that, we were doing experiments in these things, both with, physiological measures and kinematic measures and so on. And one was able to identify all the signature features of non-equilibrium phase transitions, which are the foundation of self-organization in living and non-living things. So this, again, we were lucky that by this time we were able to sort of pull the literature together and wrote a review article, and that was published in Science too. And so it really, it sort of offered a whole alternative to the notion of the brain acting as a computer, with sort of fixed algorithms and that kind of thing. And so, well, maybe I'm going on too long about this, Kenny, but the rest, as they say, is history, because there have been, there's always these scientific meetings going on, as you know, at NASPSPA is one of them, and it was very formative in my upbringing as a scientist. But there was a meeting in 1982 out in California, and it brought physicists and biologists together, and I was very fortunate as a young scientist to be invited to that. And there was a man who was supposed to be there that wasn't there because his wife at the time was very ill, and his name was Herman Haken. And he, interestingly, had written a book roughly the same time as Prigogine, called Synergetics. And Haken's theory of synergetics is that these sort of non-equilibrium phase transitions are quite general across different scientific fields. And so I'd written the paper on phase transitions and hand movements up, and I sent it to him. And even though he wasn't there at the meeting, and this is now sort of 1982, 1983, and he wrote back and said, come visit for a month, and we'll try to model this. And that was the start of an incredible experience, because Haken is called the father of laser theory. So Haken had written the first theory of the laser. He's a mathematical physicist, theoretical physicist. And the laser is a very interesting device that, under certain conditions, it gives you this long wave coherent light that's very different from a light bulb, And so this sort of light amplification process is a synergetic or self-organized process. So the laser is a classical example of non-equilibrium phase transitions in matter. And so Haken was very intrigued by these experiments on humans and human finger movements. And so I went over there, and within a month we had the theory of movement coordination by manual movement coordination by experiments of let your finger do the walking. And not only were able to describe that at sort of what was called a collective level, at the level of the coordination itself, but also at the level of the individual components, which is sort of the nervous system moving the fingers. So we were able to derive the patterns that we saw in the experiments from how the components interacted non-linearly. See, phase transitions are themselves non-linear by definition, and the components themselves are also non-linear. So these were non-linear oscillators or self-sustaining oscillators that we modeled, and the key idea is to be able to couple them together to produce the macroscopic observed effects. So this is called the HKB model, you see, and that's maybe, it's a quantitative model that is being used now for a lot of different situations, very generative kind of thing, and it's being tested over and over again. So it's a very quantitative, mathematical model of biological coordination. So that then, in terms of the kinds of people that I was working with then, with Herman Haken, started a glorious, for me, collaboration, because it sort of took me into this whole area of complex systems. And Haken had run a meeting in 1985 on complex systems and neurobiology and computers and so on. And at that time, I thought, well, gee, with all the Haskins experience of interdisciplinary, multidisciplinary work, now is the time to start a Center for Complex Systems and Brain Sciences, and that's basically what I did. And some of the core of that was actually PhD students of Haken's that came then to Florida, in Boca Raton, Florida, and I had a series of just wonderful, talented theoretical, computational physics people to work with us, you know, to get the interplay. What I think is really important in the whole field of movement behaviors, to get the interplay between theory and experiment and modeling, theory, modeling, experiment, analysis. I call it a team approach: theory, experiment, analysis, modeling. That's the four sort of components of the work. So if you can get a place where people are doing experiments that are conceptually motivated, and you have people that are interested in how to model these experiments, and then how to maybe to get the concepts very clear. For physicists, you know, it's not so much the mathematics, it's getting the concepts really clear and established and operationalized. And so that was just, you know, marvelous. And we took that into the brain, by the way, because I was always interested in the nervous system. And so in the mid to late 80s, got into the whole field of brain analysis using magnetoencephalography and EEG, you know, large-scale recordings of human brains doing these experiments, you know. So doing the same kind of simple, apparently simple hand movement experiments, or coordinating with external stimuli and so on. And of course, the beautiful thing was that we found the phase transition in the brain as well. So that was incredible, and led to then theoretically modeling all of this work. And one got even into a place where one could derive the behavioral equations of motion from equations of motion that described how the parts of the nervous system were interacting with each other. So that was, you know, just gravy, incredible, actually. So, and very, very beautiful. So that led then to sort of all the concepts and methods and tools of understanding how patterns of coordination are formed. The idea was that they're formed in a self-organized way. What conditions under which do they persist? What's the role of sensory information? You know, sensory information had been, in the days of Jack Adams' closed-loop theory, was sensory information was, you know, to build up a perceptual trace. Here we were showing, you know, with the real experiments, that sensory information can stabilize or destabilize the system with these nonlinear methods. And so sensory information was actually stabilizing coordinated states of affairs, this kind of thing, you know. So that grew into really a more general framework that we call coordination dynamics. And in a way, it brought the whole, I would say almost, you know, in the broader realm of science, the long neglected problem of motor control into sort of center field, into mainstream science as a way. In particular, what people would call in the new sciences of complexity. So does that sort of, I mean, I could go on, like, you know, Penny, as you can see, I'm pretty passionate about this. You know, there were all kinds of developments. We took this into how people learn new skills, and of course what they bring into the learning environment is what we call sort of intrinsic dynamics, modifies and is modified by the information that you want the person to learn. So that was a different kind of take. You know, you just can't learn anything. There are real constraints here, and these constraints are modified. It's what is modified. That's the process of learning. And with the late Esther Thielen, she got very interested. She came to work with me at Haskins, and then later to Florida. And she, you know, we had established all these concepts, and she just took them straight into the field of infant motor development. And of course, that has flourished as a field as well, you know, with the Smith and Thielen books and so on, Thielen and Smith books, and that whole research program. And, you know, so the implications then into fields like robotics and all the rest of it have been considerable. And at the brain level, the nice thing is that you had this sort of, if you like, sort of foundation of the so-called HKB model, which actually, mathematically speaking, has symmetry in it. And when you break the symmetry, which is what we do all the time, symmetries are broken all the time. When you break the symmetry, you actually see that the system's not fully coordinated. It's kind of relative, what von Holst actually called he called this relative coordination. The system slips in and out of coordination. It slips in and out of coordinated states of affairs. And I call that meta-stability. So meta meaning beyond stability. And in the theory, in the theoretical models, the mathematical models, what you find is that when people are asked to coordinate different parts of their body or coordinate with the environment or even, coordinate with each other, that the coordination is not sort of absolute and synchronized and stuff like that. It's much more subtle. It's a subtle blend of coming together and autonomy of the individual at the same time as the individuals working together. So that was taken also into the brain and neurosciences, and was actually people have said that's sort of a new principle of brain function, because people are talking about the brain. They ask the question always, as science tends to do: is it this way or is it that way? Is the brain a mass action coordinated entity, or is it modular? Where each part is doing some particular function. Well, the answer is it's a bit of both. And you have to actually show that and find that out. And so it's a subtle blend of the tendency to integrate, of the parts of the brain to integrate together at the same time as they have a tendency to express their own autonomy. And that principle, sort of a brain function, behavioral function, that's currently, I would say, a lot of people are interested in that. If the students who are listening to this want to read and learn about that, you Google that and you'll see where that's going, and it's very interesting, both for how the brain's organized and how it might be dysfunctional as well. Because the idea here is that, things that are too synchronized are almost pathological, and things that are too random are also pathological. So the normal is sitting in this place in between. So I called it the science of the in-between, and wrote a book called The Complementary Nature. These things are complementary, they're not contradictory. So that also alters the way you kind of look at problems. Is the brain a closed loop system or is it an open loop system? Well, actually, it's a bit of both, and it's a subtle blend, if you like. So all these dichotomies that we create are not, they're contrarieties, they're dichotomies, and that's an idealization. The reality is that it's a subtle blend of both coexisting tendencies. And that's, again, that was a bit novel at the time, but I think people are beginning to, get that whole idea of coexisting tendencies rather than either or, So, again, I could go on. I don't know how. Oh, I have gone on. I don't know if we've extended the normal.
Well, I think you've actually answered the 3 questions, or 2 or 3 questions that I had there. Actually, I'm getting a little interested in speech control. Also, I have a new granddaughter, as you know, and she hasn't mastered the complexity of ba, but she can say nana, so I'm happy with that.
Well, so pretty complicated,
well, she's doing it pretty well.
Yeah.
So I think the other questions I had was issues underlying your research and lines of research. You've certainly had many different lines of research over the years.
Yeah.
I think you've talked
I would say the main focus. The main focus has been really on the principles and mechanisms of biological coordination, and I think that sits in cognitive science, it sits in neuroscience, it sits in a lot of different fields, and that's what I like. It's really a sort of transdisciplinary topic, and it allows you, I call it the science of coordination, where from neurons to people, So that's the broad framework, and of course there are many problems within that.
Right. And then I also had questions about researchers have had an influence on you, but I think you mentioned many of those that certainly influenced you over the years. Yeah. So I think that's good. So, Scott, you haven't been at NASPA for a little while. Early on you were. So tell us just a little bit about your involvement in NASPA, and then if you can recall when you were named Distinguished Scholar, kind of what that meant to you at the time.
Right. So I think you said something about, I'm not quite sure, but it was in the 90s, late 90s. I was
1999.
1999, yeah. So I think, you see, NASPA was very formative and important early on in my career, really. And I think the work that I described to you, about the sort of dynamical approach to equilibrium seeking, which had really sprung from my doctoral dissertation, then on into the work that we did on coordinated interlimb coordination, that kind of work, and then on to the work on phase transitions and so on. So this all, I guess, accumulated in some way that whoever nominates people for this wonderful award that really saw this as, in a way, paradigm changing and this kind of thing. I mean, an important aspect of this, when these systems are about to change, as the modern jingle is, if they're near tipping points or critical points, if you're very careful with how you're doing the experiments, you can actually see that fluctuations grow in a systematic way. That's called enhancement of fluctuations near criticality. And that's another word for that is variability, and so the variabilities and fluctuations are now great sources of interest in NASPA and the field of motor behavior in general, and I think that it sort of changes the way we think about that. Variability is actually a good thing because it allows you to discover new states of affairs under the particular conditions you're immersed in. So I think that whole development of work, and as I say, I think with the papers in Science and stuff, I think somehow that attracted attention, and it was a great honor, of course, to receive the NASPSPA Distinguished Scholar, because really of the predecessors, people like Jack Adams and Franklin Henry and Dick Schmidt and these kinds of people, and so to be among that, that group was really, an all. I shouldn't really be there. It was a very honorable thing, a wonderful honor, and just with all humility. And I think, like an old science penny, this is not. I may have been nominated as an NASPSPA Distinguished Scholar, but it's clear, I think, by the descriptions of the work that it involves a lot of people, and both at the level of one's advisors and collaborators, and at the level of students. And some of my students have been most proud, actually, of their achievements. So that feeds into any kind of individual award, I think. And it was very nice to get, to be awarded the NASPSPA Distinguished Scholar. And as you say, I think maybe it's up into the mid 2000s. I was, pretty regular at NASPSPA, and then I think, just the world is really of the world of science and stuff is there's just a lot of stuff going on, and in a way, science itself is moving fast, and there's a lot of conferences going on, and researchers and down to complex systems and involving physics and biology and cognitive science and neuroscience. So sort of, I suppose, I see those as integral to NASPSPA, but of course they have their own agendas as well. So I feel that NASPSPA as an organization, and I feel that the fields of research in NASPSPA are still very, very fundamental. I think actually the movement, physics is the science of motion and change. And I have these discussions with my colleagues and friends all the time, and I'm saying, when is physics going to take up the problem of animate, living movement? And it's amazing that it hasn't. And that's the what I've been describing kind of thing as the tip of the iceberg here, because I think people in kinesiology, people who study biological movement, human movement, intentional movement, I didn't really describe the work that I've been doing recently, but I really see, look, physicists at the time of Erwin Schrödinger had said, when I move my limb, it's me doing that. I know it's me, right? So what is this I? What is this self? And a lot of my work was actually showing that you don't need to put the self in there. These things are spontaneous, and they, study the conditions under which these patterns of coordination emerge. But there is always this directed aspect in living things. This we call it intentional. Sometimes will is used. Now, how does one bring that back into the picture? How do these biological systems get directed to do particular things? And I see that as just right up NASPSPA street and the kind of young people that are coming out of the field of movement. And I think it's a great challenge. And I think, to the extent that people haven't embraced that challenge or taken it seriously as they could, let me be provocative. Let me ask, maybe a lot of things that folks take pretty much for granted are actually very deep. And certainly they haven't been studied at the level of, I'm not saying by the way to physicalize animate movement. I'm saying that animate movement is going to extend the physics. And it's going to extend the physics from the inanimate to the physics of living things. And whether those principles overlap or whether there are new principles, Schrödinger said there's going to be new principles for biology, and I believe that strongly. And I think these new principles for biology, a very good starting point is animate living movement, and that's the stuff of NASPSPA, and it's the stuff of all its journals. And I think people need to take that challenge. I get a bit preachy, I'm sorry, but they need to take that challenge really seriously if they're serious about the science. I guess I kind of like to leave it there, Penny.
Okay, well,
before I get myself in trouble.
There you go. You've been known to do that, so that could occur. Yeah. So, Dr. Kelso, thank you.
Yeah, you said where you think the field is going and stuff, and I think it's almost like it needs triggered, and maybe some of what I've said will help trigger that. Yeah.
Well, Scott, I know that we're having our 50th anniversary in San Diego this year, and I know you can't come. I believe you're going to be in Ireland receiving a major honor from the Royal Irish Academy of Science, so congratulations on that. And we're sorry you can't join us, but perhaps in the next few years, if we're in your neighborhood, you'll be able to drop in on NASPSPA and see where we've come since you've been there.
Well, thank you for the kind remark. The Royal Irish Academy actually spans the humanities as well as the sciences, and so I guess I've been elected an honorary member, and there's a very distinguished group of people that are honorary members. So this was a humbling experience. But I'm hoping, Penny, that I may get out to San Diego. As you know, I have family out there as well. So I'm hopeful that although the travel may be not be very good for my health, I'm going to see if I can shift things around in a way that I might be able to make it, because I think to be there for the 50th anniversary of this organization, I was around at the very beginning, really. One of the very first meetings I went to was at NASPSPA, and it was in Windsor, Ontario, I think. But I remember George and I together driving up to that, and stopping on the way. You know, Dick Schmidt was in Michigan at the time, and this kind of thing. So NASPA means a lot to me, and it's I'm proud to be associated with it. So I hope to be able to make it, Penny. You know, I hope to be able to.
Oh, great. Everyone would love to see you, I'm sure, so that would be super if you could. So, Dr. Kelso, thank you so much for sharing your ideas with us and your thoughts today, and we hope that others will now be able to hear some of your ideas over the years. That's fabulous. Thank you so much.
You're welcome, Penny. Very welcome indeed.
Okay, take care. Bye-bye.
You too. Bye-bye.